Hi, this is Mrs. LaBarbara. This is AP Physics, and today's topic is Newton's law of gravitation. The objectives are: know the force of gravitation is universal, and know how the value of G was determined, and know why gravity is important. Understand gravitational forces on two bodies are action-reaction pairs. Understand capital G and lowercase g are two different gravitational quantities, and be able to calculate gravitational forces between several bodies exert on each other. Newton's law of gravitation states every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. This is also called the inverse square law. Here is a diagram showing you M1, M2, and the distance is between the center of each two objects. Any two particles attract each other through gravitational forces. Even if the particles have very small, very different masses, gravitational force they exert on each other are equal in strength. This is due to Newton's third law. To write an equation, Fg actually equals to capital G times M1 times M2 over R squared. This capital G is called a universal gravitation constant, and it is in the reference table. We need to know gravitational force is a vector quantity. It has directions, so it must be combined as such. For example, if we have two objects, what is the gravitational force acting on object 1? You have to consider all the forces. This forces is combined from 2 on 1, from 3 on 1, and from 4 on 1. So to find gravity on 1, we have to add all these vectors together. Remember, when we add vectors, we have to consider directions. We have to decompose the vectors into x and y components, and then add all the x together, add all the y components together, and use Pythagorean theorem to find the resultant. The difference between capital G and lowercase g. Lowercase g is the acceleration due to gravity or gravitational field strength, which relates the weight W of a body to its mass, m. W equals mg. The value of g is different at different locations on Earth's surface and on the surface of different planets. Let's see how we can derive what g is. Because mg also, that's the weight, also according to Newton's laws of universal gravitation, equals to capital G m times big M over R squared. So as you can see, the lowercase m cancels out. So G equals to capital G times big M over R squared. This means the gravitational acceleration of the field strength only is determined by the mass that create the field. It has nothing to do with the mass experiencing the acceleration. Okay, only the mass that's creating the field and how far the location is away from the field. On the other hand, capital G relates the gravitational force between any two bodies to their masses and the distance between them. G is universal constant. That means it does not change with different mass or different location, because it has the same value for any two bodies, no matter where in space they are located. Henry Cavendish determines G. Gravitational force were relative until 1798, about 100 years after Newton stated his law of universal gravitation, when Henry Cavendish made a sensitive measurement to determine the numerical value of constant G, capital G, using torsion balance. Here is his setup. So here is torsion, a fiber connected to the smaller M1 and the bigger M2. So gravitation pulls the small mass toward a large mass, causing the vertical quartz fiber to twist. The smaller balls reaches a new equilibrium position when the elastic force exerted by the twisted quartz fiber balances the gravitational force. So in that case, he can, because those forces are the same, and he can figure out what is the elastic force, he can figure out the gravitational force. how did he figure out the elastic force? He used the angle to measure the angle. The deflection of laser beam indicated how far the fiber has twisted. Once the instrument is calibrated, this results will give us the Fg, therefore give us the big G by using this equation. Fs equals Fg when the two object is in equilibrium, and that equals to this. You can measure m1, m2, and r squared, and Fs, that's how he determines the capital G. And this capital G, as you can see, is very, very small. This is because gravity is one of the smallest force of 4 fundamental forces. Example, mass m1 of one of the small spheres of Cavendish balance is 0.0100 kilograms. The mass m2 of one of the large sphere is 0.500 kilograms. And the center-to-center distance between each large sphere near a small sphere is 0.05 meters. Find gravitational force Fg on each sphere due to the nearest other sphere. So we can use Newton's law of gravitation and substitute the numbers. As you can see, this number is very small, right? This is a very small force, which is what we expect. We don't experience noticeable gravitational pulls from ordinary low mass object in our environment. It takes a truly massive object, such as Earth, to exert a substantial gravitational force. Another example, suppose that one large sphere and one small sphere are detached from the apparatus in last example, and placed 0.5 meters from each other at a point far away, removed from all other bodies. What is magnitude acceleration on each? So we already figured out the force on each is 1.33 times 10 to the negative 10 newtons, and this is the force on both the smaller sphere and larger sphere because those are action-reaction forces. From Newton's second law, we can figure out acceleration. This is the acceleration of the smaller sphere and the acceleration of larger sphere. As you can see, the larger sphere has much smaller acceleration than the smaller sphere. This is because the larger sphere has 50 times the mass of the smaller sphere, hence 1/50th the acceleration. Note that acceleration are not constant. Gravitational force increases as the sphere moves toward each other. This is acceleration when actually gravitational acceleration when those are in equilibrium. The torsion force is balanced with gravitational force. Another example, many stars in the sky are systems of 2 or more stars held together by their mutual gravitational attraction. This figure shows 3 star system at an instant when the stars are at vertices of 45-degree right triangle. Find magnitude and direction of total gravitational force exerted on a small star by the 2 large ones. As you can see, this is a vector addition, so you have to add F1 and F2 together using the law of universal gravitation. So F1 equals 6.67 times 10 to the 25 newtons, but it is at 45 degrees relative to our x-axis. F2 is on the x-axis according to the same law, and we have to find x and y components of each force. Then we add all the x together and all the y together. Again, we use a Pythagorean theorem to find the magnitude and direction. While the total force F on the small star is tremendous, magnitude resulting acceleration is not. It's very small. And it's not directed toward the center of the mass of larger stars, but it's on here because it's toward actually. This is the common center of the mass of the 3 stars. Why gravitational force are important? Gravitational force are negligible between ordinary household size object, but very substantial between objects that are the size of stars. In fact, gravitational force is the most important force on the scale of planets, stars, and the galaxies. It is responsible for holding our Earth together and for keeping the planets in orbit about the sun. Gravitational force is so important on the cosmic scale because it acts as a distance without direct contact between the bodies. Our solar system is part of a spiral galaxy called Milky Way, right? Milky Way, so which contains roughly about 10 to the 11 stars as well as gas, dust, and other matter. The entire assemblage is held together by the mutual gravitational attraction of all matters in galaxy. So as you can see here is Milky Way, and our solar system is right over here. And it takes about 100,000 light years to go across. Test your understanding. The planet Saturn has about 100 times the mass of the Earth and is about 10 times further from the Sun than Earth is. Compared to the acceleration of Earth caused by the Sun's gravitational pull, how great is the acceleration of Saturn due to the Sun's gravitation? So remember, the gravity is Fg over me is g times the mass of the Sun divided by how far the planet is away from the Sun. And here is g of the Earth due to the Sun is this. And we know this g is inversely proportional to r squared. So if the distance is 10 times away, then g is 10 squared times less than the gravity of the Earth. So G Saturn is 1/100th of that of the Earth. What's the takeaway? So we know the force is universal between any two object has mass, and the value of G was determined by Cavendish using torsion balance. And gravity is important because that is a force that keep the solar system together, keep the Earth together, and keep our galaxy together. Gravitational force on any two objects are action-reaction forces. So the Earth attract you about 600 newtons, same thing, you attract the Earth with the same 600 Newton force. Capital G and lowercase g are two different quantities. Capital G is constant, lowercase g changes. Be able to calculate gravitational force using the law of gravitation. Another example, spheres x, y, z have masses and locations indicated on the figure above. What is the magnitude of net gravitational force on sphere x due to the other two spheres? So luckily this is just one-dimensional problem, so we don't have to decompose the components. So in this case, we simply add two vectors together because they are in the same direction. Just make sure in this case you factor in gm squared over r squared, and then you add fractions. So you should have 11 over 9 times gm squared over r squared. Another example, two identical satellite orbits a planet R of radius r in circular orbit A and C of radii 3r and 12r respectively. How does the magnitude of gravitational force Fa compare that of Fc? So because the only difference is the distance, these two have the same mass. Remember, Fg is inversely proportional to r squared, so this r is 4 times of this r. So the force would be 4 squared times less. So Fa equals 16 times Fc, and here is the math. And that's it for today. Thanks for watching.